and equivalent geometry.
Thank you very much. Thank you very much for giving me this chance to meet all the people in this math department. And then I'll be really excited to come here to work with all of you. And well, today, so the title is Orbifold and Equivariant Geometry. So I think the biggest goal today is, like, when you study Orbifold, Orbifold is not really new object. It's been studied like maybe 40 years or maybe 50 years. But recently, maybe like 10 years ago, 15 years ago, some string theory was developed in mathematics for Orbifolds. And then since then, a lot of work on some geometry set theory for Orbifold. And then when people developed all this theory, the original notion of Orbifold was really not clear language to talk about the abstract theory. So then they borrowed some language from Grothendieck, and then now people look at Orbifold as stack. So the stacky language is really important language because a lot of papers are written in terms of stacks, and then if you don't know certain understanding of stacks, it's really hard to understand. So today's goal is to give you some ideas of how stack works, and try to convince you stack is not that scary object. Okay?
Are you going to introduce stack in terms of Grothendieck style?
No. So today I'm going to talk about stack in the category of smooth manifolds. Yeah. But the definition really follows Grothendieck. But you don't need to talk about his name. Maybe one place, but you don't need to care about that. Okay. And I'll try to finish in 1 hour, but if I don't finish it, just free to leave, okay? But, okay, and then another goal is, so I've tried to calculate the cohomology of equivariant cohomology of stack in my research. But the definition of cohomology of stack is a little different from the usual topological space, right? So, and there has been a little confusion among definition of cohomology, which definition you take, and then you are calculating something different. It's invariant, but it's different. And especially over z coefficients, different differential gives you different invariants up to torsions, right? So, so once I convince you what the stack is, I'm going to define what the cohomology of stack is, and also equivariant cohomology on stack when some group acting on it. Yeah? And that will be the last goal. And if I get to that, I'll be really happy. Yeah? Okay. Orbifold. So when people define Orbifold, there are basically 3 different ways of defining Orbifold, and in terms of charts. And this proceeds like usual definition of differentiable manifold. You look at a topological space, and you find homeomorphism from open covering to some open set in Rn. And then the compatibility is the overlapping place, you have a diffeomorphism going from Rn to Rn. Right? So you have this notion of Orbifold charts, and that's the original definition of what Orbifold is from Satake in, I think, 50s or maybe 60s. Right? And then there's also a rather recent notion, groupoid. And then, so, right, there's rather recent notion of Orbifold, which is described in terms of groupoid. Yeah? And then I'll explain this groupoid in a moment. And then the third way of defining Orbifold is stack. Okay? And from here, there's a way to construct a groupoid, and then there's a theorem that from a groupoid you can construct the Orbifold chart. But in the Orbifold case, groupoid and stack is really general concept. And when you restrict your attention to Orbifold, this is something I'm going to explain, but it's proper groupoid, and it has to be a tau groupoid. Okay? So the Orbifold is like, locally it looks like a quotient of Rn by a finite group. This finite group action corresponds to those properness and then a tauness. Yeah? And then here for the stack, it has to be a smooth stack, a differentiable stack, and it has to be the linear manifold stack. And those three notions somewhat corresponding each other. Okay? Right, and I have these 7 pages of notes, and then I don't think I can finish all 7 pages, so I'm going to skip this Orbifold chart. Okay, and then just directly start with the groupoid notion. And that saves a lot of money. Not money, time. Yeah? All right, so first, what is groupoid? So groupoid is just a category with some property. And everybody's okay with category? Yeah, you have objects, and between objects you have a morphism. And then when you call it category, you have some compatibilities. I mean, structure maps between things. Okay, and so this is a category. And we're gonna put some geometry on this category, groupoid. Right? So the objects and morphisms all consist a set. Right? The collection of objects is a set, and the collection of morphisms is a set. That's called a small category. Right? And then when you say groupoid category, that means morphisms. Morphisms are isomorphism. Yep. Okay, so let's say you have a morphism, and this is object. Okay, and then so now you're looking at this collection of objects and morphism as a set, and then you can define the structure maps. I mean, that's just the intrinsic maps between x1 and x0 coming from the structure of category. Okay? So what is this? There is a source map. So you can think of an element in the morphism as an arrow from object to object. So there is a starting object and an ending object. Right? So the source map sends arrow to its starting object. Right? And then there is target map. You send it to the target of the morphism. And then there is a composition map. Yeah? The composition map, you look at the composable pair. Right? You have a you have arrow G, X and Y, and then you look at H going to Z, right? And there is a composition of those two morphisms. Right? But not all the arrows can be composed. You have to make sure that the ending target of G and source of H has to be the same thing to compose. Right? That's something you can describe it as a fiber product. So you have this source map and target map. And then those are the sets, and then probably if you forget, you can just look at the book or maybe Wikipedia what the fiber product means. So basically, this is the Cartesian diagram, and you can define this fiber product as a universal property, but also you can think of this as a, the source of this is the same as target of this. Okay? The image, when you take a pair here, the source of G and target of H has to be the same. The image of this source map and target map are the same. And that's how you construct this fiber product. Right. Now, there is a composition map from this fiber product to a set of morphisms. Okay? That's one of the, it's encoded in when you say these are categories. Right? And then there is, so it's a groupoid category, so there is an inverse map, inverting the morphism. Right? And then there is identity map. For each object, there is this identity map. Right? That's one of the axioms for the category. Okay? So you have all these structure maps. Yeah? This is x1. Right? You have an object and send it to identity morphism of the object. Okay? So this is just a category theory. There's nothing really complicated. Right? Just a bunch of structure maps, and then, okay, there are a bunch of compatibility conditions, but you forget them. When you have to check it, you look at the definition. Okay? But now we want to do some geometry on here. So let's just put the C infinity structure to everywhere. Right? So that's called the Lie groupoid. So Lie groupoid means x1 and x0. It's a smooth. Right? And all the structure maps, it's smooth. Okay? But wait. There is something other than x1 and x0, right? This. Right? When this kind of fiber product is smooth again. Right? Direct product, it's okay. It's smooth manifold, it's smooth. But you're doing something else. Right? This sits inside a direct product. Right? How do you make sure this fiber product is again manifold? What's the reasonable condition you can assign so that this is smooth? Yeah. And of course, if you don't do differential geometry, that kind of condition is not, the everyday condition you look at. So I'll tell you. So to make sure this thing is smooth, you assume source map and the target submargin. Okay? So this is the theorem. When you have a fiber diagram, one of those maps submargin, then the fiber product is a smooth manifold. So when you define Lie groupoid, you want to have a smooth manifold here too. So you assume source map and target map is submargin. Okay? So that's a little subtle condition you have to say when you define Lie groupoid. Yeah? So this condition is needed that all the structure maps is smooth, right? So you need a smooth structure here. Okay? That's it. Right. So somehow the orbifold is given by this kind of Lie groupoid.
Example of groupoid.
Yeah, okay. Yeah. So example, the really important example is when the Lie group acting on the manifold. Yeah? Lie group acting on a smooth manifold. Now in this case, there is a canonical groupoid you can construct. It's called action groupoid. Right? So the space of arrows, it's just the direct products of G and M. Yeah? And the set of objects is just the points of M. Yeah? So you have G, X, and you have to define the source map and target map. The source makes X, and target makes GX. Yeah? So it's like you have M.
G, what is the morphisms? X1. What is the morphisms in this case?
So this. So I didn't write the notation. When you look at this groupoid, the notation is this. Yeah? When I write this way, it means a groupoid. Yeah? So G cross X is X1, and M is 0. So the space of objects, that's M. And then you look at points, and those are the objects. And what is the arrow? Arrow is the action. Right? But action, there are many.
The group element sending X to Y.
Yeah. Arrow. And then here is another Z to W, and there is another G here. This arrow and this arrow are different, even though it comes from the same group element. Right? So you sort of put the information of the source too. So those are the honest arrows in this groupoid category.
So this pair, GX,
is a morphism. Yeah. A morphism, you need where is the source of the morphism. You need where is the target of the morphism. Yeah. So you have to specify where the source is. Yeah. So this is the wrong thing to do. Okay.
Why T is so much?
Hmm?
Why T is so much?
Why T is
So much.
sub.
You should example of legal way.
Yeah.
Why T?
Why T is
Submargin.
submargin. Yeah, submargin is when you look at the differentiable map, differential, right? The map on the tangent space. And forget this G. M to M. So let's choose just one point here, identity. Right? So M goes to M, and you take a differential. Tm goes to Tm, and it's obviously search submargin. Some tangent space of G, cross tangent space of M goes to this. Yeah, and this is surjective, right? The map on the tangent bundle being surjective, that's the definition of what the submargin is. It's surjective.
I'm curious about that. People imitate the theory from string theory. This is source map and target map. That seems to be an analog of the source space and target space, which can be characterized by the partition function in string theory.
Maybe some groupoid structure in that context, but I have no idea what string theory. Yeah. I mean, this is really general notion. Like, groupoid category, it's really general. It appears sort of in all kinds of mathematics. It's just that sometimes you're just not using this word. This is really general object, and still the Lie groupoid is really general objects. So now the question is, what kind of orbifold? I mean, what kind of groupoid corresponds to orbifold, right? So proper, and proper means that x1 goes to x0 cross x0. This is source map and target map. This is proper map. Okay, and et al. The et al. Is a word coming from, I mean, we use this et al. A lot in algebraic geometry, but not in a differential geometry, because we call this a local diffeomorphism. Yeah? So the groupoid is et al. If source map and target map are local diffeomorphism. Okay? And for the latter notion, let me define. Okay, so you look at this groupoid and take x from little x from x0, and gx called the stabilizer in this groupoid. So this is another notation for this. Okay. So how do you define this? This is the set of morphism going from x to x. So this is G in x1 such that G, the source of G, equal target of G. Okay? So this is like, so you look at this x1, the space of morphism, as some action on this x0. And so this action stabilizes this morphism stabilizes this x. Yeah? So the source and target of the morphism is x. Yeah, so this space of morphism, part of the space of morphism fixes this object. Okay? And this is called stabilizer. And for these conditions, etalness and properness, the etalness says this is discrete group. Yeah? And then properness says this is finite. Okay? And this is because this is a kind of fiber in the diagonal. So it has to be proper, it has to be finite if it's discrete. Yeah? Okay, so the idea is, so orbifold is defined by proper A, proper, et al. Groupoid. Okay, and I haven't really discussed what the chart is, but the chart is you start with a topological space, and then you have this local chart. Locally, it looks like a finite quotient. But so now remember when you define a manifold, right, you have a open covering, and in each open set is homomorphic to Rn, right? And that's called atlas. Right? But then, if you look carefully, a manifold is defined as equivalence class of atlases. Okay? So there are two different atlases, but they might define the same manifold. So this equivalence class, equivalence relation in this orbifold chart is really complicated. Well, it's not that complicated, but it's kind of pain to describe everything. So idea is having one proprietor groupoid is like having one atlas. Right? But in the atlas side, there's this equivalent notion, equivalence relation notion. Right? So how those equivalence notion define equivalence relation for this groupoid. Yeah? So there is certain equivalence relation among groupoid, and then Orbifold is defined as this equivalence class of a proprietor groupoid. Yeah? So for that, let me just okay. So before that, let me just introduce some other notion of this equivalence of groupoid. Okay? So first, so this x to be x1, x0 modulo x1. Okay? And I started with a proprietor groupoid. Okay, so because all the morphisms are invertible, the space of morphisms define equivalence relation among objects. Okay? And then take a quotient, and then the quotient has a quotient topology. And when you have a proprietor groupoid, this quotient is nice topological space. Well, I'm not going to go into this niceness, like paracompact blah 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 space. Yeah? Okay, so somehow a groupoid defines the Orbifold structure, Orbifold atlas on this topological space. But then if you take another groupoid, it defines equivalent atlases, and then you want to say two groupoids are equivalent. Right? And that's called the Morita equivalent in the groupoid theory. So first, a morphism from X to Y, it's just a functor. Right? Between groupoid, the morphism, the natural notion should be a functor because groupoid is a category. Right? But we have this geometric structure, the smooth structure. So we need to assume, so let's say this functor is phi, and phi is a map from x0 to y0, the corresponding objects, and also morphism goes to morphism. Right? Those maps to be smooth. Yeah? So that defines the morphism of Lie groupoid. Okay? And then so when you learn this, when you learn things about category, there's this equivalence of category, and it wasn't equivalence, right? There wasn't the inverse of equivalence of category. The equivalence is always one direction, right? So two categories are equivalent when there's a equivalence in one direction, but it doesn't mean that there is a equivalence in the other side, and that's because it's a complication about this object category. Right? It has object space and there's morphism space. So that's why sometimes you can only define one direction isomorphism of categories. Yeah. So how do you define two groupoids? Well, anyway, so the equivalence is really a morphism, which is equivalence of category. Okay, but it goes to only one direction. Yeah, but so now how do you define the equivalence between two categories? Right. This equivalence only gives you one direction. Like it's not the symmetric relation, right? So in this case, how do we sort of extend this non-symmetric relation to equivalence relation? You define the equivalence extending this one-way relation to equivalence relation this way. If there exists the third groupoid and equivalence to x and y. Okay? So that's it. So two groupoids of Morita equivalent if there's a third Lie groupoid and there's an equivalence to x and y. Okay, and I forgot to mention that the equivalence of Lie groupoid is just the equivalence of category, but I forgot to mention about the compatibility with a smooth structure. So there's compatibility for C-infinity structure. Okay, it's not so important now, so I'm not gonna write these conditions, but there is. Yeah? Okay, so now the orbifold. Say x. So orbifold there is always underlying topological space, so let's call x is defined as Morita equivalence class of a proper et al. Groupoid. Okay, and it's not really nice because this is really bad. You want to work when you do some geometry. You need to do some local things, right? Local chart, and you want to work it. But then, say you are given this orbifold, and then you do some things, right? But then you have to make sure that whatever you calculate here, it should be the invariant under this equivalence. So you have to check all these calculation for all other groupoids, which is Morita equivalent to that. But then there is no map, direct map. There's always, there might be just third map, or maybe right. So you're looking at this, you do some geometry here, but then you have to make sure that this computation is the same as the computation you do here. But then you have to go through all these things. There's no direct map like that. So it's really hard to compare the computations in a different presentations. So that's the biggest problem of study of orbifolds. Okay? And there, Grothendieck comes in and tell you this is how you do it. Okay? And so now I'm going to move on to definition of stack. Okay? Okay, so to talk about stack, I need to motivate. So I attended like a school on stacks like maybe 6 years ago in Germany, and the lecturer was Kai Barendt, William Fulton, and Andrew Kress, all these stars in algebraic geometries. And that school was really good because even though I wasn't an algebraic geometry, I didn't understand all the details, but they gave me really good understanding of how stacks should be viewed. Okay, so today, even though it's videotaped and then all the people in the world can see the video if they want, but I might say a lot of wrong things. But my goal is convince you that stack is not so scary, so that if you have this good idea, you can look at the published paper and then understand sort of big picture, so that you have motivated to look at the details. Okay, right. So this is third way of defining orbifold. You have to get used to this notion of stacks. Right, so motivation. So motivation is really the moduli problem. Okay, so moduli problem is you have some objects you want to study, yeah, and you want to classify that, and then you want to find some space. You want to look at the, so this is really find a space to classify some objects you want to study. So say even surfaces. Okay. Right. So first thing you do is a set. You look at just this set, right? And all Riemann surfaces, and then you divide by isomorphisms. So basically, you're looking at the set of isomorphism classes, Riemann surfaces. But this is just a set. And how do you do geometry on this set of isomorphism classes? Yeah. What is there anybody like ideas? Okay. I give you study this and find a space to classify. And how do you sort of study this set? Geometric structure. Professor? Yeah. So I think when you study something, first you look at locally and then do some understanding of local things. So you fix one object that you are interested in, and then you look at what kind of things, what kind of other objects are close to this object you're looking at. So first you do local geometry. Right? So how do you do it? Right? Consider deformation. Okay? So you fix one object and then you try to deform the structure you're interested in. Okay? Well, what do you mean? Yeah? So this deformation is really a family of the object you want to study. Right? So you look at, so this is the space, right? And then you look at the families. Okay? And then maybe here you fix the objects, and then you look at how the structure you're interested in it deforms. Okay? That's a local geometry. So when people say deformation theory, yeah, so they are looking at this, how much direction you can deform, and in some direction are the same, right? So you have to quotient it. You're looking at the tangent space of this. Yeah? So that's the local geometry. So you start with one family of some objects you want to study, and then you try to understand the local picture, how things are deformed, like tangent space. Yeah? So this is really analytic problem. Yeah? But now you want to do, so this is local geometry. Okay? But now you want to do a global geometry. So you want to construct, you want to look at this set as a global object, not the local object. So what can you do? You consider all families. Okay? Not the single one, because single one gives you some local geometry. But you have to look at all the families. But that is a category. Right? You look at all the families, and it has some structure of categories. Yeah? But I mean, this is still really bad, because you want to do geometry, and now you're looking at the category. I mean, how can you play geometry for a category? Yeah? So now we need to do global geometry for a category. Yeah? So this is where the Grothendieck comes in. Grothendieck started with the category, and then he explains how you can start doing the geometry for a category. So what kind of category can be studied geometrically? Yeah. So then there's 3 steps until you can do complete geometry for the category. And then the first step, you show that this category is a category 5 origin groupoid. And the second, you show that it's a stack. And this is like this is just like a 0th step. Yeah? You're looking at the family, so there's this 5 version of the category. So that I'll explain in a moment. But this is not really geometric. But here, you start putting some topology for a category. And this 3rd step, you show the stack is C infinity. Yeah? So there's 3 steps. This is just a setup, And here you start topology, and here you do geometry. Okay? So there is a direction here, categorical, here, geometrical.
What is the first step?
The first step, a category 5 ring groupoid. But I'll start explaining 1, 2, 3 now. Okay. Oh, and then maybe this fourth step, if you want to do nicer geometry, you have to say it's a Deligne manifold C infinity stack. Okay, and this is where you can do. This is called Orbifold. Right? So there are a bunch of layers. Okay, and then each step you have to show some axioms. And then when you got here, you're looking at Orbifold, which is really similar to manifold. It's an Orbifold. Okay? So this idea of looking at the stack as a family of objects you want to study, and that was really a big breakthrough for me to understand what the stack is. And actually, this is just one way of looking at the stack, and there's another approach to define stack. It's called you start the sheaf theory on a category with Grothendieck topology, and that's really a different way of looking at it. It's like this is more like differential geometry way of looking at the stack, and then when you look at stack as a sheaf over a category with topology, that's more algebraic geometry approach. Yeah? So some textbook start with this sheaf of groupoids. That is the pre-stack kind of thing. And that direction I'm not really familiar with. But some other textbooks start thinking about stack this way. So not really perfect today. Okay. So let's just start. So this, studying this Riemann surface is really classic problem, but it's still really difficult, right? It's not really a toy model to understand stack. So I'm going to give you another example of family of objects you study, which gives you really good understanding what the stack is. So give you example, definition. So let's say G is Lie algebra, a Lie group. Okay. And what is the G torsor? Are you familiar with the G torsor? And it's just a set where G acts freely and transitively. Yeah?
G, what did you say?
G, this Lie group, G torsor. It's a set where G acts, maybe it's a topological space where G acts freely and transitively. So like G itself, right? But G torsor doesn't have a group structure, right? So it's just some representation of G in a category of sets. Yeah? So it's a space, maybe a set, a topological space, maybe a manifold, where G acts freely and transitively. And I don't really need to introduce this name G torsor, but somehow this textbook of stacks, they use this G torsor all the time. Okay? But really, now I define a category BG, and when I write BG, this is a classifying space. Okay? But I'm defining something else. It's a category. Okay? It's not the space. So object, it's a family of G torsors over a manifold. Okay? And let's put the quotation mark. And what could this be? Really, some geometric object you're familiar with. Yeah, you have a manifold, you have a fibration, and each fiber is a G torsor, so it's a topological space where G acts freely and transitively.
This one?
Yeah, principal G bundle. Right? So you look at the category of principal G bundles, yeah, and the morphism is really clear, right? So the object is like P over U, okay, and here is the G action, okay, and the morphism is the bundle map. The bundle map is really a pullback diagram or Cartesian diagram. People, whatever you call it, pullback, or it's the same name, Cartesian diagram or fiber diagram. Okay, so you have a category of the principal G bundles, right? Okay, so this is really the basic example of a stack. So we're going to follow all the axioms by looking at this category of families of G torsors. And you can replace these G torsors, whenever you want to make a different stack. Okay? Stack is a family of some objects. Okay? All right, so now what is category 5 within groupoid? So it's a category X with a functor, a category 5 within groupoid over the C infinity. So this is the category of manifold. Okay? So whenever you talk about the stack, you have to choose the geometry you want to work in. Either manifold, a smooth category, or algebraic category, or even topological category, or you can do set category. And maybe not that good. It's not good. You need a topology at least. Yeah. So today I want to focus on the C infinity category. So everything is C infinity. So there is this base category where you work. Right? So the category 5 in groupoid is a functor from a category to this base category. Okay, such that. Right. So now I need a functor, right? So there is a BG to C infinity category. You look at the principal G bundle, and you're looking at the family over a manifold, right? And base category is the place where you do geometry. So you're sending this the base space, okay? And for the functor, you need to send the morphism too, right? So you have a diagram, and then you send it to the underlying map. Yeah, the bundle map there's underlying maps on the level of the base, right? So this gives you a functor. And that's the functor which makes this BG as a category 5 within groupoid. But what's the condition? Yeah? Condition 1, there is this pullback. Yeah? So pullback is what, right? When you have a morphism in the base category and an object, so you have an object, okay? And then there is a morphism at the base category, and then there exists, so let's say this is F, and there exists a pullback. Yeah? So basically, when you look at this category as a category of families of some objects, so you fix one family of objects, and then you take a map on the base space, and then you can pull back this family. Yeah? That's the condition, one of the conditions for category 5 within groupoid. Yeah? And then when you say pull back, more technically, it has to be unique up to a canonical isomorphism. Yeah? And yeah, that's true, right, for principal G bundles. And another thing, is when you have So I'm going to try to write all the axioms in words, yeah, so that you have an intuition of what the axiom is. But when you actually look at the textbook, text is not that nice. Okay, it just gives you with a bunch of notations. But really, the meaning of each axiom is what I'm writing here. Okay, so the first condition is pullback exists, unique up to canonical isomorphism, and that's what happens for categorical principal G bundles, right? And now another thing is when you have a morphism in this category of families over identity map is an isomorphism. Do you think you get the meaning, right? So when you have a P prime and P, those are the objects, principal G bundles, and it's over U and it's over U, not the U prime. Right? So if there is a morphism, and then the underlying morphism is identity map, then this bundle map has to be isomorphism. Yeah? And that's another axiom for the category 5 order groupoid. Okay? So this is really natural conditions for the category of principal G bundles. And when you try to understand general category of families of groupoids, you can try to assume those, you try to prove those natural conditions for good families so that you can get closer to some geometry structure on the category. Yeah? But the model is really a category of principal G bundles. Yeah? Right, so that's it. The category 5 in groupoid, it's like a category of principal G bundles. There is a pullback, and also if you have a morphism over identity map on the base, it has to be isomorphism. Yeah?
What do you mean by canonical isomorphism?
So, like a pullback is not unique, right? But once you have a pullback, there is a not canonical isomorphism between them. That's really the universal property of pullback. So you define pullback. I mean, you have to look at it's a universal property of the fiber diagram. So there exists a space here which makes this fiber diagram. It's by universal property. Universal property is if there is a thing here which goes here and here in the commutative, and there is a unique map here. But then this also has a map. If this is a pullback, then you can replace the role of this, and there is an inverse canonically. So there is a diagonal isomorphism between them. Yeah? So it's really just the universal property of pullback. Pullback diagram, fiber diagram. All right, so now we can talk about stack. Right? And this is the fastest introduction to the stack. Yeah? So category 5 in groupoid X is a stack if there is a 1, 2, 3. Okay? So as I said before, category 5 in groupoid is still really a category. But now, when you talk about the stack, you need some topology. You're going to start doing some geometry. So the first thing is topology. Yeah? And the topology comes from topology for manifolds. So we define this notion of covering family of M, which is manifold. So that's this is local diffeomorphisms such that the union goes to M surjective. Okay, and it's called the covering family. And you can, right, so the example is when you have M and then when you have open covering. Open covering is not just a local diffeomorphism, but, well, it's a local diffeomorphism, right? Right, so the open covering is a covering family, but somehow you allow this covering to be actual covering. I mean, local diffeomorphism. You can have some ramification, yeah, some number of sheets, but locally it has to be diffeomorphism. So this data, then you can define this in the category of manifolds, right? For each manifold you can define this. And this notion tells you C infinity category has a grothendieck topology. Okay? So his notion of stack is much more general. You can start with any category, and if that category has this grothendieck topology, you can do geometry. Okay? So you can consider a stack over that category with a grothendieck topology. But we are doing really explicit C-infinity geometry, so this is really a fixed topology we are given. So you don't need to look at the axioms of grothendieck topology for category. Yeah? You just have this notion. Okay? So this notion of stack uses this covering family, or you can think of it just as open covering too. And there's no difference between considering open covering and this covering family. And this covering family is also called the étale cover. Yeah? And in algebraic geometry, considering the open cover and considering étale cover are different topology. But in C-infinity category, they're the same. That's what they say. I haven't checked. Yeah? So in C-infinity category, it's okay. Yeah? And the notation Uij, if they are open cover, it's the intersection, right? And if they are étale cover, you have to sort of generalize the notion of intersection, and that will be the fiber products. Yeah? Okay, so now you can study the local property, how the local property becomes global property for families of objects you study. Right? So the first axiom is locally identical morphisms are identical globally. Yeah? So basically this covering family gives you a way to understand the family locally, because open sets are local thing. Yeah? And then you have two morphisms of principal G bundles, and if you look at those maps, bundle maps locally, if they are identical, that means globally they are the same maps. Right? So it's good. Yeah? And the second thing is we can glue local morphisms you can glue local morphisms to a global morphism. Yeah. So you have so you have two objects, and then you have a morphism between objects locally. Now, if you restrict this morphism, if you have two objects, and then you restrict those objects on the open set, and suppose I give you the morphisms on each open set. Yeah? How can you glue those local morphisms to globally? You need a compatibility, right? compatibility is what? Right? These local morphisms agree on the intersection. Yeah?
Restriction is pullback.
A restriction is pullback, right? Restriction is pullback by inclusion. Yeah? So that's what this is. So you need the compatibility on the intersection, right? Intersection. If they agree on intersections. Yeah? I'm really talking about natural things for principal G bundles, right? But I'm just making explicit all the properties. I'm making it explicit so that we can abstract it. Right? Okay, so now we show that all two different morphisms, they are identical if locally identical. Right? And now you start with the local morphism and you want to glue it to a single morphism, global morphism, if they agree on the intersections. And now we need to construct the global family from a local family. Yeah? We can glue local objects and local families. Right? Objects are families in the stack, right? We can glue local objects to a global object if they are isomorphic on intersections. Right? So this is the transition functions of the principal G bundles. You've defined the principal G bundles as a trivial bundle locally, and then how can you glue to a global G bundle if they are isomorphic on the intersections? This isomorphism is specified by transition functions. Right? Are isomorphic on intersections. Yeah? So it's sort of amazing, like bunch of abstract objects, like a lot of notations in the textbook, and then if you understand it, that's what these are what they are saying. Okay, so what I was explaining was BG is a stack. Okay, the categorical principal G bundles, that's a stack. And this is called a classifying a stack of G. Okay. It's a categorical construction of classifying space. Classifying space is a topological space, but it's bad because it's infinite dimensional. Right? But classifying stack, it's a category, yeah, so it's still bad, but it's a much easier construction of classifying thing. Yeah? Okay. Right. So let me give you more examples of stacks. So stack should be a generalization of a manifold. You haven't really put a smooth structure. All right. Yeah, so putting a smooth structure needs a little more work. So before that, I'll give you more examples. Right? So we want to generalize a manifold theory to a stack. Right? So manifold should be a stack. How? So start with a manifold, and we need to categorify a manifold. Okay? So what is the object? Object is all the morphisms, all the maps. So infinity maps from any other manifold. Okay? And the morphism?
U is any other?
Yeah, any manifold. Yeah? And I'm spreading a big pot, right? Well, that's how you start abstract things. And then you throw away a lot of things. You don't need this, you don't need this, you're just thinking really small things. But this is sort of how things are done in algebraic geometry. You sort of start with the big things and then sort of narrowing down what you have to look at. Yeah? So you look at all the maps from all manifolds. Right? It's a huge things. Right? And then what's the natural morphism between those maps? that should be a commutative diagram. Now, I'm saying stack is a family of objects. And what kind of object you're looking at here? So you have to look at this u to x as a family of something over u. Right? This is an object over u, so it's a family of something over u. U to x, and then you have u. So this object in the category is a family of something over u, right? So what's the fiber? Yeah? You look at this, a point, yeah? And what's the fiber? Fiber is a map from a point to x. What is it? It's a point in x. Right? So it's a family of points in x over u. Yeah? Okay, right? Right. So that's how you look at the manifold as a stack. Yeah? And those axioms, you can pull back. Pull back is just a composition, right? And yeah, I think if you just look at these things carefully, it's really trivial. Okay, so this is really important. All right, so now it's done. Okay, right. Okay, so maybe, what should I do? Yeah. Any questions? So you want to, right. Okay, so maybe in 5 minutes, I'm going to explain how you put the smooth structure on this stack. And then in September, I'll come back and continue the same, this talk. We're going to just start it over. All right, so number 3. So number 3, you need so the stack is differentiable. I write C infinity, right? Right, so we want to do some global geometry for a stack, right? And to do global geometry, we need to put some global C infinity structure associated to this stack. And so you have to go back to the idea of moduli problem, okay? And there are 2 conditions, and then the guideline is this, right? You can play geometry for moduli space if you have a universal family. A universal family classifies all the objects, and the universal family is a family over some manifold or maybe algebraic variety, and then each fiber corresponds to object you study. So there's a bijection between each fiber to each object you study. Yeah? Then that's how you do geometry for the moduli problem. But not all the moduli space has this universal family. Yeah? So to play geometry for stack, you have to check that there exists a versal family. Yeah? And what is the versal family? All other family can be constructed by gluing gluing the local families that are pullbacks from the versal family. Versal family, I write this way. Yeah, this is the base manifold, and this is the object in a category. So this is the big family of objects you classify. Yeah? And this is not universal family, so because maybe some fibers can be the same isomorphism class, right? So that's why you don't call it universal. Versal means that it gives you all the objects as a fiber, but maybe some objects are identified. Yeah? And if you identify those fiber, isomorphism fiber, the base space is no more smooth manifold. So that's the kind of case you have to consider. Universal family is very nice. Each fiber is not isomorphic to each other, but it's not going to be the case in general. Right? But more important property is universal family is all the family is a pullback from universal family. Yeah? But for the versal family, that's not going to be true. You just want to construct every family locally as a pullback from the versal family, from X to X. And another thing is, this is not the only condition for a stack to be C infinity. So now you're looking at this versal family, right? And then there is a way to construct a groupoid. Yeah? So the objects is just the underlying space, and the morphism is somehow you identify the morphism is all isomorphisms of fibers. Okay? So this is a natural groupoid structure you can construct from a versal family once you fix the object you want to classify. Yeah? But then how can you make sure this is actually a Lie groupoid? This X is a manifold, but if you collect all the morphisms of fibers, it might not be a manifold again. Then you fail. Yeah? So you have to construct this X1 as a manifold again, and that's a really strong condition. Yeah? And so for stack is a family of objects you want to classify, and then there is a universal, the versal family. That's one condition, and then from versal family you have to be able to construct the Lie groupoid by looking at the morphism space as a set of all isomorphism of fibers. Okay? So now we call it a presentation. Is this groupoid of X to be the objects of that presentation is the underlying space of the versal family, and this morphism space is the set of all isomorphism of fibers. Okay? So now you have a C infinity stack, and the C infinity stack you can always choose this presentation. This is where you do a global geometry. Yeah? But so here, by looking at this Lie group, you can do geometry, but then sometimes there's a different presentation, and then if it comes from the same stack, then those are Morita equivalent. That's the big theorem. Yeah? So the Morita equivalence class of Lie groupoid corresponds to a stack, and there's a way to construct a stack from a groupoid, and it's just the same construction as this BG. You generalize the notion of principal G bundle for Lie groupoid, principal Lie groupoid bundle, and that gives you a stack again, and there's one-to-one correspondence. This for symphony stack, you get the Lie groupoid, and then if you construct the principal groupoid bundle, you get the original stack. That's another theorem. Okay, sorry, I took 13 minutes more.